Hello, Terry here. Today I want to show you a how-to example of an improper integral, something called Frullani integrals. All right, so just a quick reminder, right? If you remember from your first year calculus, when you take integrals, whenever one or both limits, goes to either positive or negative infinity, then you have what they call a type 1 improper integral. So this here, because one of the limit is infinity, so it certainly has a flavor of type 1 improper integral. But you also remember there's something called type 2 improper integral. Type 2 improper integral is when your integrand, in this case, the integrand involves 1 over x, and 1 over x is not continuous at this limit 0. All right? So these are called point of infinite discontinuity, right? And so this is a type 2. So when you have both type 1 and type 2, these are called mixed type of improper integral. So here are 3 examples of mixed type improper integrals. E to the minus 3x minus e to the minus x over x. All right? Integral of going from 0 to infinity, inverse tangent of ax minus inverse tangent of bx all divided by x, all this. Now, some of you watching this here may say, well, wait a minute. How do you know these integrals even exist? In other words, are they integrable? Again, that is not the focus of this video, right? So here, we are not going to be concerned with whether they're integrable or not. We assume they are all integrable. We assume that you're dealing with, situations in which it is integrable. What we want to know is how do you evaluate this quickly, right? Because sometimes when I glance at a problem, I wish I know exactly what the answer is going to be very quickly without doing a lot of work. So can we do that? And it turns out that, under certain circumstances, you can. So let me introduce you to this. All right, so if you look at all these examples, right, they all have one thing in common. Namely, they all have this form. Some function f of ax minus the same function f of bx, all divided by x, integrate from 0 to infinity. Whenever you have a form like these are called Frullani integrals, named after the Italian mathematician Giuliano Frullani. Okay, so what I want to do here today is I want to show you that under certain circumstances, all right, you can actually, look at this and get to an answer very quickly. As it turns out that whatever f is, as long as it satisfies 3 conditions, integral of this form all have the same structure in their answer, namely alpha minus beta log of b over a. Let me explain what they are. What is alpha? Alpha is when condition number 1. So after you identify the function f, if it satisfies condition number 1, when t goes down to 0, f of t has a finite limit alpha. Condition number 1. Condition number 2. When t goes up to infinity, the function f of t has a finite limit beta. And condition number 3. Whatever f is, if its derivative is continuous from 0 to infinity, right? If those 3 conditions are true, then for all a, b positive, a, b being fixed constants, as long as they're positive, then the integral from 0 to infinity of f of at minus f of bt over t, i.e. the Frullani integral, always equal to alpha minus beta times the log of b over a. Always. All right? So let me just quickly prove this. All right? So, when you're dealing with the integrand, having problem at 0, a standard way of proving this is fix an arbitrary little number l, just right above 0. So that way you avoid, the problem of the integrand. Second, you don't want to mess with infinity yet. Let's just go and fix an arbitrarily large capital L. Fix a arbitrarily large capital L. And then consider this integral from little l to big L. So little l is above 0, so you don't have to worry about this part here. Big L is fixed, so it's not improper. So this integral is just an ordinary definite integral. Okay? So now, under this format, excuse me, let's make a substitution. Let u equal to a times t. Okay? Then when t is little l, u is a little l. When t is big L, then of course u is a capital L, right? Now, u is at, so the first part here is just f of u. Now, the second part is bt. So if you solve for t here, is u over a equal to t. So bt becomes b over au. B over a times u. Okay? And then the bottom, right? Remember, if u is at, du is a dt. Okay? du is a dt. So this at the top, right? So this becomes du over u. Okay? All right. So now, here comes the second part of the proof. And this is important. Here's an important trick. Let gamma equal to b over a. Whatever b and a is, I have no idea what it is, right? So let's let gamma be b over a. Now remember, a and b are positive, so gamma is positive. Now define this function. The integral from little al from a little l to a big L of f of u minus f of gamma u over u du. After you integrate this with respect to u, this function, whatever the answer is a function of gamma. So that's why I'm going to define a new function called h of gamma. But I'm going to carry along little l and big L because I'm going to need to use that later on, right? Because remember, little l and big L are arbitrarily set at the moment. So using the third condition, with f prime being continuous on 0 to infinity, by Leibniz rule, if I were to take the derivative of this function, it's the same as the derivative of this integral, which I can pass the derivative inside. Now, hold on. Let's stop, right? Let's make sure we understand what we're talking about here. You see, this integral is with respect to u. Whatever it is a function of gamma. I want to differentiate that function with respect to gamma. So what I want to do is I want to be able to simplify this process. And the way to simplify this is if I can pass this differentiation inside, meaning instead of integrate first and then differentiate, wouldn't it be nice if I can differentiate first and then integrate? Well, it turns out you can't just move the derivative inside without some justification, okay? And that justification is guaranteed by something called Leibniz rule. So remember, I'm not gonna get into Leibniz rule, so look it up, or just look it up what it means. But the point is, Leibniz rule allows me to pass the derivative inside. So in other words, change the order of operation. Instead of integrating first, then differentiate, you want to differentiate first, then integrate. And the requirement is f prime being continuous. In other words, as long as f prime is continuous, I can do this. Okay, now let's look at inside. Let's just focus on the integrand. All right, what's happening here? You see this integrand. The first term is f of u over u. The second term is minus f of gamma u over u. The first term, f of u over u, insofar as gamma is concerned, is a constant. In other words, when I want to differentiate with respect to gamma, f of u over u is just a constant. So what's the derivative of a constant? 0. So in other words, this first part, I can just drop it because the derivative of f of u over u with respect to gamma is 0, and integral of 0 is 0. I can just ignore it. So all I have left is just the second piece, which is the derivative of minus f of gamma u over u. Let's work that out. What is the derivative of f of gamma u with respect to gamma? Well, it's the derivative of f of gamma u, d gamma u, times the derivative of gamma u, d gamma. Now, let's focus on the second piece. What is the derivative of gamma u with respect to gamma? So remember, you are differentiating gamma u with respect to gamma. So u is just a constant. So gamma u is the same as u gamma, right? And what is the derivative of u gamma with respect to gamma? It's just u, okay? So this second piece is just u. This first piece stays the same, df gamma u over d gamma u. Okay, now continue. Substitute everything back. Now noting that gamma is positive, what is the derivative of this function? Remember, we dropped the first term, is negative integral from a little l to a big L, d gamma f of gamma u over u. But what is df gamma u over u? We already worked that out. That's df gamma u over d gamma u, du. Okay, now from this second line to the third line, I'm going to multiply and divide by gamma. Remember, gamma is positive. I can do that. So if I multiply instead of du, I'm going to have d gamma u. And then here, I take a 1 over gamma outside. So you're good. Remember, gamma is constant at this point, right? So when you do that, this becomes minus 1 over gamma, integral from a little l to a big L, df gamma u over d gamma u. Stop. So at this point, you might say, wait a minute. Somebody watching might say, oh my God, what does this mean? I know what du is. I know what d gamma is. What is d gamma u? Well, as it turns out, in undergrad, you learn most of the math you learn is something called the Riemann theory of integration. It turns out that there are more advanced form of theory of integration, one of which is called Lebesgue-Stiltier theory of integration. As a data scientist, I work with probability a lot, and in the world of probability theory, almost all integrals are Lebesgue-Stiltier integral. So either you look it up, learn it, or if not, just take my word for it. D gamma u is perfectly fine. So basically, in the Lebesgue-Stiltier world of theory, in the Lebesgue-Stiltier theory of integration, it doesn't have to be a variable du. It could be the entire function. So for example, I can have dq of u, dq of u, or d some function of u. Okay? So gamma of u is just a function of u. Right? It's a constant function of u. So d gamma u, believe it or not, is legit. It's actually legitimate. So just take my word for it, and we'll continue. All right, so this becomes minus 1 over gamma of this integral. But now hold on. If you remember in undergrad, even in first year calculus, they talk about something called the fundamental theorem of calculus, which says that when you integrate a derivative, it's the same as the antiderivative of that function, or the original function, evaluated at the upper and lower limit. So here is df of gamma u. So imagine let v equal to gamma u. So this is df of v over dv. So and then dv. So the integral is just f of v, evaluated a l and b, a capital L and a little l. So this is f of a capital L minus f of a little l, all multiplied by negative 1 over gamma. Perfect. So at this point, I have gotten rid of u through integration. All I have left is this little l and big L. Okay, let's tackle that. Remember, a is positive and fixed, right? That's a given constant. So as little l goes down to 0, remember I arbitrarily set it, where is it? I arbitrarily set it to be above 0, right? So now, when I let little l goes down to 0 from the top, as it goes down to 0, a is constant and fixed and positive. AL goes down to 0 as well. But we were told that this function is such as it goes down to 0, it has a finite limit alpha. Similarly, as capital L goes up to positive, remember capital L is also arbitrarily set, right, somewhere. So as I let capital L goes up, A is positive and fixed, so AL also goes up. And we have also been told by second condition that this function is such that f of something goes up to infinity is beta. It has a fixed limit beta. All right, great. So now, in other words, all of this is just beta. This is just alpha. So it's beta minus alpha. So it's negative. So in other words, this derivative here, after taking this limit, letting little l go to 0, big L go to infinity, is just minus 1 over gamma, beta minus alpha. Minus 1 over gamma, beta minus alpha. Okay, let me rewrite that a little bit. Remember, is beta minus alpha with a negative sign. So let's get rid of that negative sign by turning this around, right? Making it, instead of beta minus alpha, let's make it alpha minus beta, so I can get rid of the sign. So this becomes just alpha minus beta, d gamma over gamma. Okay, now, because this is a differential, right? So this is the derivative on the left. This is a function on the right. So I can integrate both sides. Remember, gamma is positive. I can integrate both sides from from 0 to infinity. Then in this case, this integral now becomes 0 to infinity. So this is my original Frullani integral. That turns out to be just the integral of this with respect to gamma. And you guys remember, right? D gamma over gamma when you integrate is log gamma. LOG is natural log. I know. Some people use ln. I like to use log. To me, in my world, log is natural log. Anyway, so integral of this is just log gamma. Well, what is gamma? Gamma is b over a. So in other words, the Frullani integral, when those three conditions are met, is just alpha minus beta all times log of b over a. QED. That's the proof of this theorem. So we can now use this as a tool to solve problem. All right, let's quickly take a look at an example. Going back to the beginning, when I listed the first example, we want to integrate this from 0 to infinity, e to the minus at minus e to the minus bt, all divided by t, where a and b are fixed positive constant. How do you integrate this? Well, look at this. If you just eyeball this function, right, you can kind of say that, yeah, let f be e to the minus t, right? If f is e to the minus t, then this is f of at, this is f of bt. Okay, if f is e to the minus bt, e to the minus t, right? Since e to the minus t is continuous at 0, so when you take the limit as t goes to 0, f is just f of 0. And f of 0 is e to the minus 0, which is e to the 0, which is 1. So alpha is 1. What about beta? Beta is letting t goes to infinity. When t goes to infinity, e to the minus t gets smaller and smaller and smaller and eventually vanish. That's 0. So beta is 0. Okay? So alpha is 1, beta is 0. So alpha minus beta is 1 minus 0, or 1. All right, third condition. If f is e to the minus t, f prime is derivative with respect to t is minus e to the minus t. Now, of course, minus e to the minus t is continuous everywhere. So certainly it's continuous from 0 to infinity. And so all three conditions are met. Apply my main theorem earlier. This Frullani integral is just alpha minus beta, or 1 minus 0, which is 1, log of b of a. In other words, it's just log of b of a. That's it. That's the answer. Okay? Look at another example. Another example. Suppose a and b are fixed positive constant. Find the integral from 0 to infinity. Inverse tangent of at minus inverse tangent of bt, all divided by t dt. So again, just eyeballing is pretty clear. You want to let f of t be the inverse tangent of t. Now, remember, the inverse tangent function of t is continuous at 0. So the limit as t goes down to 0, or alpha, is just 0. Because that's just inverse tangent of 0, which is 0. Similarly, the tangent function is such that as you approach pi over 2 from the left, you're going to go to infinity. So therefore, the inverse tangent is such that when t goes to infinity, its limit is pi over 2. I mean, it's exactly backward. So therefore, you know, when t goes up to infinity, inverse tangent of t is pi over 2. So in other words, beta is pi over 2. So alpha is 0, beta is pi over 2. So alpha minus beta must be 0 minus pi over 2, or negative pi over 2. Okay, now third condition. If f of t is inverse tangent of t, f prime is derivative must be 1 over 1 plus t squared. Again, those of you who have taken trig function and trig calculus, calculus or trigonometry, you should know this, right? The derivative is 1 over 1 plus t squared. 1 over 1 plus t squared is a very nice function to work with. It certainly continues everywhere. In other words, nowhere in the real line you will find problem here, right? So certainly the derivative is continuous from 0 to infinity. Great. All three conditions are met by the previous theorem. It must be minus pi over 2 log of b of a. That's it. Minus pi over 2 log of b of a. Okay? All right. Let me give you an exercise. Think of this as a challenging exercise. You know, see if you have time, if you're interested, see if you can figure this out. Suppose P and Q is greater than 1. P and Q are some arbitrary constant greater than 1. Find the integral from 0 to 1 of t to the p minus 1 minus t to the q minus 1 all over log t. Now, notice just this current form is not Frullani. Just forget the rest. Right? Look at this limit. It's 0 to 1, not 0 to infinity. However, right? Obviously, that's why this is a little bit of a challenging exercise, because you need to do something about that to turn it into this form. So even though this, even though this, right, by itself, that is not Frullani. However, it can turn to Frullani. I'll leave that to you as an exercise. How do you do that? And once you turn into Frullani, go ahead and apply the theorem, and your answer should be log of p over q, where p and q are positive constants greater than 1. It should be log of p over q. I'll let you work on that as an exercise if you like. Thank you for watching.